So now I have combined all of them, okay. So this is called as maximum likelihood estimation, okay. So now how do I find the parameters? Now remember, this is now a complicated function, it is a function of log, it is not a function of simple function like a square minimizing square that you can take a numerical differentiation and solve it. I mean you can just analytically take a differentiation and solve it, okay. So and remember, it is also a non-linear function, unlike equals to y equals to mx, you have y equals to probability of y given x equals to 1 by 1 plus e power minus z, and z itself is a function of thetas, theta transpose x, okay. So there are 3 levels involved: logarithm function, exponential function and z. You understand? First ln of probability of y given x, so logarithm has to be first differentiated, then probability of y given x is what, 1 by 1 plus e power minus z, and then z itself is what, theta transpose x. So there are 3 layers, 3 levels involved, okay. So differentiation at 3 levels have to be done, okay. And remember, as he was mentioning, the function is not going to be smooth, it is not a smooth function like a convex function, only a one bowl, it is not going to be smooth, it is going to be a bumpy or non-convex or non-smooth, okay. So there is no guarantee that you will find a global minima etc, it will be very difficult because it is not going to be smooth. And on top of it, remember your neural networks, how many neurons do you think it has, each has? If I talk about ChatGPT, I told you 153 million parameters, okay. So you can imagine the number of neurons, even in your simple network you will have multiple. Anybody had experience with working with deep neurons? How many layers and how many neurons? Huh? ResNet 50, that itself 50 layers, and you can think of neurons in each layers. So we are talking about some 500 600 neurons easily. How quickly you want to solve? You want to solve for days, hours, months, you want in minutes results, right, you want as quickly as possible, right. And today the deep networks are so deep that it even takes whole bunch of time for training, okay. And you want algorithms to be faster, you do not want a slower algorithm, and that is where we use what is called gradient descent for solving of this kind of minimization. So you want to minimize this function, but we will do a quick and dirty method, which is what followed today. Every neural network, all those run this only gradient descent. Of course there is no guarantee that you will get a global minima, that is why there are so many networks for the same problem, because it is non-linear and you never know whether you will get a global minima or not. So nobody knows which network is better, that is what the truth is, nobody knows which network, which problem it is better, but there are so many, because one of the key reason is this the methodology to obtain the global minima is called gradient descent, and it is not useful for, it cannot find out global minimas. If there is only one minima, it will find out, if there are multiple minima you will get some minima, okay. I will explain this gradient descent in a simple fashion, okay, without lot of math, okay. Very simple, one diagram should be enough to explain this. I will take a simple case to explain it. Let us assume there is a bowl, the parabola, where is the minima? Bottom. Now does not matter you stand left or you stand right up to the bottom, you are on the left or right of the bottom. Now if you are left on the bottom, what is the direction of the gradient? You all know what is a gradient, what is the difference between gradient and the slope? Y equals to m1 x1 plus m2 x2, is m1 and m2 gradient or slopes? Variation in the rate of change in the direction of the variable is what is a gradient. Usually slope, because there is only one number, one variable, dy by dx is slope, dou y by dou x1 is gradient, because it tells you the rate of change in the direction of variable x1. If I do dou y by dou x2, it tells the variation of rate of change of y in the direction of x2, okay. So that is the difference between gradient and the slope. Slope is absolute differentiation, there is no multiple variables involved. When you talk about Gradient, it is usually partial differentiation, and you are talking about the rate of change of that particular variable with regard to another variable x1, x2 and x3. So that is why you do partial, then you get gradients. Okay. Now as we talk about, we are solving a general problem theta transpose x, where x is a vector, so you could have many variables. So what is, and you, that is what usually the case, you usually have many inputs, right, you do not give only one input for a neuron or neural network. So you have multiple inputs, so you are, so suppose here W is a vector, keep in mind W is a vector. So suppose I stand in this x wherever I marked, what is the rate of, what is the gradient's direction? Huh? Gradient direction is bottom, which direction the slope is increasing? Which direction is the gradient increasing? Top, right? If you keep on going, the curve becomes actually straight, so the slope is, rate of change is pretty high. So the direction of the gradient is what? Opposite to that of the bottom. Remember, take a bowl, okay, if you go in this direction, gradient is increasing, if you go in this direction, gradient is increasing. That is why I said you have the second derivative to be less than 0 for a minima, the second derivative to be greater than 0 for a minima, because in both the directions gradient is only going to be increasing. Okay. So whether you stand on this side or whether you stand on this side, the gradient direction is going to be pointing upwards, whereas where is the minima? Bottom, opposite to that of the gradient. Where is the minima? The minima is opposite to that of the gradient, and that is why you call it as gradient descent, not ascent, descent. So you are going to go in the direction of opposite to that of the gradient, that is what you do. If you want to find a minima of this function, cross entropy or log likelihood function, or this can be applied for any objective function, you simply need to take a gradient and go in the opposite of the gradient. So now my new weights, so you are old weights, so if you want to call it as theta, weights, it does not matter. In machine learning language they call, instead of j they call it as L, this is called loss function. In your in our jargons we call it as cost function, in statistics and others we call it as cost function, in machine learning we call it as loss function. Here we have theta as the parameters, and in machine learning we have W as the weights. These are just jargons, both are equivalent. Okay. Now I want to know the weights or the parameters, both are one and the same, right. I have showed you the equivalent. Now the new weight or new parameter is nothing but, you assume whatever you want to, you start with whatever you want to, that is old weight, you assume randomly, and what should I do? I should go in the negative of the gradient, negative of the gradient with respect to what? The loss function or the cost function, dou j by dou theta. Understood? Agreed? I am going in the direction opposite to that of the gradient to reach a minima, and of course I can keep it, I can have a tuning parameter called alpha. Why? This alpha always lies between 0 to 1. If alpha is 1, what does it mean? You will just immediately go. If alpha is 0.5, you are moderating the growth. So if there is too much alpha, what can happen? Same function, you are here, if alpha equals to very large, you can jump here, you can jump here, etc. Right? If alpha is too small, you can go slowly, you will get a lot of time. Okay. So there is some optimal alpha, we do not know what is optimal alpha, there is some optimal alpha which will take you to the minima faster. Okay. And this alpha in machine learning jargon is nothing but your learning rate. Okay. So these are terms which you will hear here and there, but you know this is what logistic regression gives you idea about neural networks and neurons. So alpha is nothing but your learning rate. I can only go in the negative direction of the gradient. 1 itself I will jump. 0 means no learning, 1 means just going opposite of the gradient. Why should I accelerate? What is the benefit? You think that direction is the optimal? I do not know any direction is optimal, right? So that is why I always have between 0 to 1. It is found that even 1 is bumpy, usually 0.3 is a good number. They also call it as forgetting factor, etc. Learning rate, forgetting factor, so many to that. If I combine this alpha with another parameter so that I can do what I call, here you are only concentrating on the current gradient, right. I can take past gradients also into account. If you take past gradients into account, that is called momentum. This is all machine learning terms used today in every neural network. They will say momentum as a parameter. Momentum simply means it depends on the past gradient. Remember, here we are only doing on the current gradient. The problem with current gradient is you may be stuck in a local minima. Now instead of doing that, if you give a push using momentum which depends on the past gradients, then you may not get stuck in a local minima, you may move towards a global minima. So momentum is another parameter. It is all common sense. Current, just looking at the current gradient, instead of looking at the current gradient, you think on the past gradients also. That is momentum factor. Okay. So there are several variations to gradient descent, but this is the vanilla gradient descent. Okay. So now see, I have not touched turn one turn left. Okay. I have actually did every step by step. Okay. You can see I have written in handwriting. Okay, and scanned it and kept it. So this you will not see in books. I have derived bit by bit. Okay, so now how do I apply gradient descent for our problem? That is the question. You all understand what is gradient descent. You go in the negative of the gradient, alpha is your parameter, you can set it to be 0.3, etc. Now how do I apply it to the logistic regression problem? As I said, there are 3 layers. What is it? First, the log function, then your 1 by 1 plus e power minus z, then your z. So if you want to do 3 levels of differentiation, remember this is all dependent upon differentiation. 3 levels of differentiation, what is it? How do we do? Chain rule. Okay, chain rule of differentiation, you all remember? Okay, so first year, probably first year or 12th class or first year mathematics, that is what? Chain rule. I have did chain rule here. Okay, I have derived bit by bit. So remember, dou L by dou W, oh boy, okay, dou L by dou W1, that is what the first parameter is. This is what, this is nothing but dou L by dou pi or dou y hat. Okay, I have written y hat as A for whatever, I did not want to write every time y hat, so made it A. So dou L by dou y hat, that time I thought A is there. So dou L by dou y hat and dou y hat by dou z by dou W1 or dou theta 1. This is my 3 levels of chain rule. So I have to do dou L by dou y hat, because loss function is what? Loss function is minus y ln y hat minus 1 minus y ln 1 minus y hat. So the loss function is only in terms of y hat. Okay, so that is why the first step is to do with respect to y hat. And what is y hat? So y hat is in terms of z, and what is z? W1 x1 plus W2 x2 blah blah blah, right. So that is why 3 levels of differentiation, clear. So now the first level I have did here, dou L by dou W1, you can differentiate, what do I have? Minus y ln y hat, this is nothing but dou by dou W1 of minus y ln y hat minus 1 minus y ln 1 minus y hat. You can differentiate this, you will get minus y by y hat plus 1 minus y by 1 minus y hat. You can differentiate this. Okay, that is what I had. Okay, and the third one is easy, dou z by dou w1 is what? Dou by dou w1 of w1 x1 plus w2 x2 whatever. So you will have only x1. Okay. So the third one is easy, the first one is not bad. The second one is slightly complicated, dou by dou z of y hat. Okay. This I have taken help from books. So this is where derivating the sigmoid function. Basically you are differentiating the sigmoid function. Y hat is nothing but sigmoid function. So I have differentiated sigmoid function, it is nothing but sigmoid into 1 minus sigmoid, that is nothing but y hat into 1 minus y hat. Okay. Now if I put all three together, I have an equation for update equation, dou L by dou W1. When do I stop the updation? I can keep on updating. When do I stop it? When there is very little change in the value of the parameter, or when there is very little change in the slope value, then you say I have completed. That is what iterations are about, right. So this is my update equation. So I have given derivation for step by step. Nowhere in any of the books you will get this. Please notice, you will not get it in any of the books, because they will stop logistic regression at this junction and then say this is the cost function, you have to minimize using gradient descent. I have not only did gradient descent, but I have also showed you, derived you each and every parameter. Okay, clear. So this is my update equation, and not only that, I have given you a numerical problem also. This again you will not find it in books. Okay, so I have given a numerical problem. So this is my model, okay, and probability greater than 0.5 you 1, and if it is less than 0.5 0. Okay, so this is my class 0, class 1 values, and I initially take random values, okay, because weights have to be initially randomized, parameters are all random. I have taken all of them to be 0, okay, then used my predictions, I got the prediction to be 0.5. Why I have taken 0 is that will lead to a confusion point, okay. Then start training, okay, I use this update equation, look at this, I use the update equation, I got the next set of weights, okay. The update equation is derived, we have derived the update equation, I use that, updated it. So after 10 iterations I get 100% accuracy. This is simple logistic regression problem of 2 classes.